Now we'll be looking at the Chapter 4 notes on page 4, and we'll be talking about solution stoichiometry with titration. In this problem, which is very similar to the one before, we're going to be titrating an acid and a base together. Instead of two salts making a precipitate, we're going to have an acid and a base making water. But it's the same basic equation. So we're going to write the balanced equation for this first of the reaction between HCl and CaOH2. HCl is aqueous and a strong acid from Hickel-Hibber-High. Calcium hydroxide is a strong base from like of the strong bases. So this is going to be aqueous. Then it's going to make water, H2O, which is HOH in the double replacement reaction. You could write it either way. And here's calcium chloride, which again you have to make neutral because you could tell that calcium is a +2, chloride is a -1. Now you're going to need to balance the whole equation. So you're going to need to put a 2 in front of the HCl and a 2 in front of the water. Now they're giving you a molarity and a volume of HCl, so you would write molarity equals moles over liters and solve for moles. So we're going to do a stoichiometry with this. So I'm going to write the 0.150 moles here. Now you don't really need to set up an ICF chart for limiting reagent because the amount of CaOH2 is what you're trying to find. So you basically just need to do a bridge or stoichiometry to find out the moles of this. So you're going to do 0.150 divided by 2 times 1, which is going to be 0.075 moles. So that's how many moles of calcium hydroxide you would need. So what you're going to do is you're going to write that many moles over here, 0.075 moles. And now all you have to do is solve for the volume, which will come out to be 0.075 liters. And so you know now that you would need 75 milliliters of the 1 molar CaOH2. Now you need to find the concentrations of all the ions in the beaker at the equivalence point. The equivalence point is when both of these moles match up according to the stoichiometry. So now you would need to do the ICF chart. You have 0 of this, 0 of this. This is going to both run out. These are both going to run out at the same time. Minus 0.150, minus 0.075. You will make water in the ratio that is given. So 0.150 divided by 2 times 2 is that. You will make calcium chloride in the same ratio. You could even take the 0.075 divided by 1 times 1 and get this. So when you're all done, you're going to have 0.075 moles of this. You will have 0.150 moles of that, and both of these ended up running out. So now you're going to do your leftover ions. You might want to recall that the OH over here has 2 in the calcium hydroxide if you want that in your picture. And I'm sorry I messed up the charge of this calcium. It's a +2. So now let's find all the leftover ions. Well, what are the choices? The choices are H+, Cl-, calcium, and hydroxide. So let's start with the calcium. In the beaker, you have no calcium left over here, but you do have calcium left over here. So you're going to write 0.075 for that over the total volume. The total volume is the sum of 1 liter and 0.075 liters, which is 0.175 liters. So you do the math for this, and you're going to get an answer of 0.43 molar. We'll go, I guess we can go 366, 0.429. So 0.429 molar is going to be that one. All right. Put an extra 0 there. Now chloride. No chloride left over here. We do have chloride here. So 0.075. However, 0.075 times 2, because this has 2 chlorides per formula unit. So you're going to put 2 times 0.075 divided by the total volume. So that's going to be double the other concentration, which is going to be 0.857. Now we're going to look for H pluses. There are no H pluses here, And this doesn't count because it's a liquid, and liquids will not dissociate. So this H plus is going to be 0. And then the hydroxide, again, ran out here. And there's no hydroxide here because that's water and it's a liquid. It's not going to dissociate, so that's a 0 as well. So this problem is exactly like the one before, except we made water instead of an insoluble salt. And in fact, both ions here ran out because you see we had 2 that ran out with the reactants. In the other problem, only 1 ran out, so only 1 ion ran out.